Okay, I want to give you a brief introduction to matrices. Now, matrices, that's plural for matrix. Matrix in mathematics is something like this. It's a rectangular array of usually what we're going to do is work with numbers, a rectangular array of numbers, expressions, symbols, just a rectangular array. And this array is characterized by rows and columns. Like now, the rows go this way, okay? So you can see this one has 3 rows, and columns go up this way. This one has 2 columns. So we would describe this particular matrix as a 3 by 2 matrix. We always do the rows first. How many rows by how many columns? So this is a 3 by 2. And usually we refer to a matrix with an uppercase letter, usually A, B, or C. That's what you'll typically see. So we have A equals this 3 by 2 matrix. Now, this matrix here, B, is a 3 by 3. Notice it has 3 rows and 3 columns. And when your rows and columns are the same, we say that's a square matrix. So that makes sense. So this is a square matrix. This matrix, notice it has 1, 2, 3, 4, 4 rows, but 1 column. So it's a 4 by 1. This is a column matrix here. And then we have a 1 by 2. See, 1 row and 2 columns. Okay, so that's a 1 by 2. So just some definitions about how our description of how we talk about matrices. We talk about them by their rows and columns. Now here we have a 4 by 4 matrix, and it's got a diagonal here. Now it's got a diagonal going up this way too. But this coming from left down to the right like this is the main diagonal. So when you hear someone talk about the main diagonal, this is what they're talking about. You start up here at the top left and you just go down this way, straight down. Now notice all the elements on the main diagonal have this, they're in the same row and column position. So for example, this is position 1, 1, row 1, column 1. Here's row 2, column 2, row 3, column 3, row 4, column 4. See? So numbers on the main diagonal have that. They're in the same row and column number. Now sometimes you'll see a matrix like this where you have the main diagonal and there are just zeros below that main diagonal. When you have a situation like that, we call that an upper triangular matrix. Likewise, if the zeros are above the main diagonal, we call that a lower triangular matrix. Now, when we have, so I want to look at some operations of matrices. First is just the addition. When we have a couple of matrices defined, if they are the same dimensions, in other words, both of these matrices are 2 by 2s, then we can add them and we can subtract them. In other words, we can say, okay, I'm going to talk about A plus B. And we define that to just be you add the corresponding elements. So notice this 2, add it to this 2. This 5, add it to this -3. This 9, add it to 8. And -7, add it to 6. And you can see that here. Now, if we talk about subtraction, it's exactly what you would think. Now you're subtracting. So you take 2 minus 2. See? 5 minus a -3. Now you have to really watch your bad self because when there are negatives involved, it's easy to make a mistake. But remember, it's 5 minus a negative. So that's going to be 5 plus 3. And so forth. 9 minus 8, -7 minus 6. Now, so that's pretty straightforward. Also, scalar multiplication. We're going to look at 2 types of multiplication. Scalar multiplication, that's when we just multiply the matrix times by a number. And then matrix multiplication, where we multiply 2 matrices together. But here, we're just taking a number, just a number, a scalar, and multiplying by A. So for example, we might see 3A. Well, what does that mean? If you think about it, 3A is just A plus A plus A, and which is this. And you know what this means. We know how to add this. We just add corresponding components. 2 plus 2 plus 2, 5 plus 5 plus 5, and so forth. So it looks like this. Or another way to look upon that is you have 3 times 2, 3 times 5, 3 times 9, 3 times negative 7. So here's the thing. When you're working with scalar multiplication, all you do is multiply everything in the matrix by whatever the scalar is. So in this case, it was 3 times 2, 3 times 5, 3 times 9, 3 times negative 7. Now, addition of scalar multiples. So let's suppose we have a couple of matrices and we want to calculate this, 3a plus 2b. Well, the first thing we do is we take care of the scalar multiplication. It's just like it's the order of operations, right? You do multiplication first before you do addition and subtraction. So we do the multiplication first, and notice what we have. We have 6 plus 4. See, dig that. 6 plus 4. Then 15 plus negative 6. See, we just add the corresponding components then, and we get this. This is addition of scalar multiples. Now, let's look at matrix multiplication. So we have a couple of matrices here, and we want to multiply them together, a times b. Now, here's the thing to remember about matrix multiplication. Generally, a times b and b times a are not going to give you the same result. In fact, you could have a situation where a times b will give you one thing and b times a does not even exist. We'll look at that in just a second. But remember, a times b and b times a, not necessarily the same thing. They can be, but generally they're not going to be. So here you have a times b. Now notice, when you multiply two matrices together, you get another matrix. Okay? You're going to get another matrix. And it's going to have these components. It's going to have position 1, 1, row 1, column 1 position. Look at this one. See the little subscripts here. Row 1, column 2. Down here, this is position row 2, column 1, row 2, column 2. So that's how we can read these subscripts. Now let's look at how we would multiply these together. To get this C11 right here, I'm going to take row 1 from this matrix A, see, and multiply it by column 1 of matrix B. Now, what I'm going to do is I'm going to distribute this row 1 through here completely, and then I'm going to distribute row 2 through here completely. But first, I take row 1 times column 1. Now, you might say, well, how do you multiply those? Well, you multiply corresponding parts. 2 times 2 plus 5 times 8. See, the first component times the first component, plus the second component times the second component. In this case, you get 44. Now that's, we multiplied row 1 times column 1, so we're going to get C11. Because we got C11 from row 1 times column 1. See, row 1, column 1. Now, if we want row 1, column 2, I'm going to take row 1 again. Notice, same thing, but this time I multiply it by column 2. See that? So, position 1 by position 1. Position 2 by position 2, multiplying. And we get 24. So I put that up here. Okay, now we have distributed row 1 through. Now I'm going to distribute row 2. So here we go. I want this position C21. I'm going to take row 2 by column 1. See, row 2 by column 1. Multiply 9 times 2 plus negative 7 times 8. And I get negative 38, and I put that up here. Now one more I got to do, C22. Okay, 9 times negative 3 plus negative 7 times 6. Negative 69, I put that up here. So there is our product. There's the product of A times B. Now if we did B times A, we would get different matrix. But now, let's look at this one. Let's look at another example here. If we talk about multiplying these two matrices together, now notice A is a 2 by 2 and B is a 2 by 3. Now remember, when we multiply, we take the row by each column. So this times this, this times this, and this times this. So we're going to say 2 times 2 plus 5 times 8. Now notice these match up. The column here, there's 2. Okay, so this row here, each number matches up with one number in this column, right? So let's think about what that means. These numbers here in the middle have to be the same. The columns in A have to be the same as the rows in the same amount as the rows in B. So because they match up, right? You have to say 2 matching up with this 2, 5 matching up with this 8. If there was another number down here, it wouldn't work. So you have to have the number of columns over here matching up with the number of rows over here. You see that? It has to be the case. Now, if that happens, then you are going to get a product. You're going to get a matrix. And the matrix that you're going to get, we'll call it C, is going to be a 2 by 3. In this case, notice, this is a 2 by 2, this is a 2 by 3. The way we determine that it would be a 2 by 3 is the number of rows comes from the number of rows of A, and the number of columns comes from the number of columns of B. Now that's something you can explore a little bit to see why that's the case, but this is a very quick way that you can see the dimensions of your product. It's the outside numbers, 2 by 3 in this case. You determine if you can multiply the two matrices together by looking at these middle numbers. Okay, if the middle numbers are the same, you can multiply. What's the size? Well, the outside numbers. Now, look at this. Let's suppose we want to do B times A instead of A times B. Well, dig this. These numbers are not the same. So think about it. If we tried to say B times A, look what would happen. We'd say 2 times 2 plus negative 3 times 5 plus 4. What about 4? 4 is left out. So that multiplication wouldn't exist. So we can't multiply those two matrices together. So you have to be careful before you proceed to multiply matrices together.